So I'm very glad to be here and very grateful for the kind invitation from Roland and also Pavlo and Zhang Cao. This is also my first time to Sweden, so it's very nice to see such a heavy snow. Because I was in Shanghai, it's a place without such snowing in the wintertime. So today I will talk about why I was involved in the AI science or machine learning. So basically, I was trained for surface science or theoretical calculations in heterogeneous catalysis. And for a long time, we actually using DFT calculations in the 20 or 30 years ago. But now we know it's become very important to advance to see how we can modeling such larger, say, heterogeneous catalysis and also, say, reaction condition at a different temperature, pressure, and electrochemistry conditions. And also the material complexity at different surfaces, interfaces, and also we want to treat different long-time dynamics reconstruction. So basically, the system is large, and also we have to get a very high accuracy because there are reactions. We know reactions have a very small barriers. Say small differential barrier will give you very different kinetics. So I goes back to about something like 15 years ago. I was involved in electrocatalysis, and also I see Zhang Cao and several different speakers talking about this topic. At that time, we implemented this Boson-Boltzmann equation to try to simulate the reaction at the interface. So we know it's very difficult in DFT to calculate reaction at the interface, but with this one, you can modeling the implicit solvation of reaction at the interface. But eventually, it turned out to be this kind of method can only give you a trend, not a very accurate reaction kinetics. So basically, at that time, we only do the charge transfer, say also some field kinetics, give you the basic trend of the electrocatalysis. The major problem for the implicit solvation is it's not accurate enough. There are parameters and also cannot respond rapidly or very accurately to the change of the electrical potential and also the proton induced direction. So at that time, I think we have to move on to something more realistic, for example, like say AIMD or something like something more accurate calculations. So basically, at that time, I said we need to think about our basic problems. For example, how to make this faster and how to say get the sampling of the potentials fast. Basically, in the electrochemistry conditions, the question is how to use some kind of MD simulations to get the say partition function of your complex system. So now with the AI method, we know actually we replace this kind of equation or function as some kind of numerical model. And this data, we need to get something from DFT or from some experiment. And then use this kind of data, you infer your model and use your model to regenerate some new data. And eventually, you actually solve the problem without knowing exactly what's really going on. So this is interesting. So AI scheme. In Chinese, we also have this kind of old saying, so one stone, two birds, very similar to English sayings. So about 10 years ago, I started to think about we need to into this kind of catalysis work. And the first thing we want to add something new feature for our code, basically the global issue of the neural network potential. The code we said is LASP. So how we come into this area, because we found a method, we can use this kind of method to find the transition state and also find the different minima we call the stochastic service working method. It is a global optimization method, and it's quite simple. Basically, it's something kind of like metadynamics, but in this case, we do not do the explicit MD simulation. We only add in Gaussian, but we then do the local optimization, and one by one, and after some 15 or 10 different Gaussian, then we need to relax to the bottom, remove all the Gaussian. So with this kind of scheme, you can see a concrete molecule here, and this molecule will be rotated and squeezed, and eventually you can see a fast chemical reaction to occur at this very short time of simulations. So this SF method gives us the hint. We now have a good method to explore plane surface with a faster speed, and also we can see chemical reaction with much faster, say, time scale. So here is the plane surface. We compared SSW simulation with MD simulation for some kind of solid state, say, simulation like a titanium oxide. And you can see SSW give you a large area of plane surface, but MD simulation only, say floating around near the, say, equilibrium. So basically, we can see there are many reactions, and metal atoms move and OH bond breaking using SSW. And this method can also be extended to, say, in general, to different aperadical or molecular systems. You can see the glucose molecules in a short time. You can see different bond making and breaking. And basically, this does not give you, say, the exact barrier, but give you a very good data set for you to learn. So the question about like 7 years ago, what I'm thinking is, can we use the AI technique to learn this kind of global plane surface? So particularly the global means we start from some random or scratch, which like this kind of carbon-16, different carbon atoms very randomly distribute on the surface or on the vacuum, in the vacuum, and eventually they group into a carbon-17 fluorine. And you can also see metal atoms or clusters floating around the surfaces, and also solid state electrolyte and also molecular reactions. So as though so many different area and different directions, and the system size change from small to large. And we have tried to, say, develop our method. So based on this kind of SSM global plane surface data, and then we start from 2017, and eventually we have called global neural network potential, which can be used to replace this kind of DFT calculation to give you the energy and the kinetics. I would like to mention that at that time, this area is not so popular as now we see today. At that time, not so many people have the data set, and not so many people have the code ready. And nowadays, now we have more than 300 different G-MBNN potentials, and we can do up to 7 elements for material system, and we can explore many different reactions, like less than 3 carbon atoms on all the metal surfaces. So this code is very like this kind of scheme. You have the electronic calculations and also AI calculation to give you the energy and the force. And you have the geometry part to find the transition state, do MD simulations, and also other different Monte Carlo. And the training part is here. So we use a slightly different neural network compared to the typical atomic-based neural network. Basically, we add something behind this kind of output of the feed-forward neural network. So for each neural network, we output a series of parameters. We call this as atomic features. So instead of using the graph network, we use this kind of simple Bell-Pinello style of atomic network. But we, instead of using just one output, we output a series like a vector. We call this vector as atomic information. And we then use many different explicit many-body function to group all this data and to generate the total energy of the system. And this scheme can be then going deep. So you can go in one layer by one layer using the PTSD, which is the input layer of our first row net, which is the atomic layer. And then we can use this kind of many-body functions to output a series of vectors, and then we go back, and then we can eventually have quite a deep neural network scheme. And for the power type descriptor at that time, so it's about 2017, we are very naively saying, because we are knowing the hydrogen atom, say, wave function, at that time I said that we need to use some very similar wave function of hydrogen atom. So this kind of wave function or descriptor actually happened to be transferable to many different schemes later invented by many other groups. For example, we use this kind of spherical functions and also this kind of power type functions. And also we design some 4-body and 3-body descriptors. So for this kind of many-body functions, we use this kind of different, we can write many different force field like equations, this 1-body, 2-body, and 3 bodies, and also going on. And particularly, I want to emphasize that because all these equations use some parameter from the previous neural network potential. Basically, it's a parameterized many-body functions with some neural network potential give you the atomic information, and then you can use this one to generate the total energy. So, for example, in solid state, we are very interested in the doping or defects of the big solid material, and it's very difficult actually to get the energy right. For example, there is oxygen vacancy here, another oxygen vacancy here, and this 2 oxygen vacancy is about more than 10 angstroms away or even longer. And using the traditional force field or neural network potential, typically the cutoff radius is too low. You cannot see these to each other, and the scheme without this kind of many-body functions can give you a very large error. And we can do this kind of 1-body, 2-body, and eventually we can linearly get this done. And this approach actually is a very computational cheap and also can be used very general to chemical reactions. So for example, this 22-Baker system, and with also some glucose reactions, we can see the green is the one without the many-body functions, and the yellow one is the one with the many-body functions. And we can also use this scheme to compare with some very established method in the field. For example, Shanghai. I believe many speakers have mentioned this one. And Dimmerlet very recently with some equivalent descriptor or some kind of vectors scheme. And actually, we are very interested in this energy, like free energy, entropy. And you can see in our code, we can get a very similar accuracy with this kind of very, actually, I said it's a large parameter and very difficult to use in GPU, and our code in CPU. And also, we also compare the transferability with our model. For example, this is blue one is our one, red one is the Dimmerlet, and this is the CV curve for us, blue one, and this is Dimmerlet. We use our potential to fit QM9 only with less than 20 atoms, and then we do the prediction for the atom number above 20 to 29, and you can see the blue curve generally is better than the red one. So the challenge is, what we really want to do is the big system, large system with a good accuracy, and we want to do a long-time simulations. So here is the latest version. We work very hard with my colleague, Zhi-Pann, to make this code fast, because there are so many tricks in the code. And now we only achieved this kind of linear scaling to something like 10,000, 100,000 atoms. And in the last week, we make this 1,000 core peroration. And in 1 week, we can do 1 nanometers, 1 nanoseconds. And with this kind of program, we can now do this very famous strong metal support interaction for the platinum nanoparticles supported on titanium. In experiment, if you say using some hydrogen to treat this system, because it's reductive, and the experiment TM will see the titanium oxide will grow up, or we can see the grow up onto the nanoparticle. Now we can see in real time. It's very interesting to give us the idea how big of the system we can go. So LASP have some basic feature which is different or not available from other code, because this code is written fully by Fortran and C++ by our own group. So we can do SSW, and this one is the one to search structure and search reactions. And we can have our own many-body neural network potential, and we have our PTSD, we call the power type structure descriptor, and we have many elements to fit to get a global neural network potential. And with this kind of potential surface, now it's possible to do many challenging tasks. In the past 3 years, our group have several different subgroups. One subgroup is working on the interface. It's a solid interface. We try to understand the semiconducting material like silicon oxide, how they grow together, and what's the interface. And in catalysis, this is particularly important. We want to understand the grand kinetic simulation and the surface. And also we have a method to find the chemical reactions. This code has been used and registered by many other groups users, and also we work with several companies, also Chinese company and also a French company, and they are really interested in the material properties. And the basic work for my group is to generate the global neural network. For example, zirconium oxide, they want to understand the different porous zirconium oxide under the solution and the different electrolyte solutions, and we do this for them. And there are many other groups to publish many good papers using the LASP code. Basically, our website has this kind of element information. The blue one are the ones we have generated some G-MBNN potentials. So with this code, actually, in the following, I will just give you a scan of the work has been done in my group for catalysis. Basically, now we do not rely on DFT. We actually reshape the scheme to do catalysis or do some kind of simulation. So basically, in my group, we first need to do some, if we want to do a new project, we normally do some initial assessment using some energy resolved database, which has been generated by ourselves with this kind of neural net potential. And then if this one is not enough or not very accurate enough, we then generate our own G-MBNN potential. And we do not rely on particularly the experiment. We can do everything from the simulation. So we basically, from the material, from the bulk, predict the bulk material and predict the surface under reaction conditions. And when we do the reaction pathway sampling, and finally do the microkinetics. So at this stage, you can then ask the experiment or compare with their result to what's really going on in experiment. So I give you some idea of this energy resolved database. We generate this kind of silicon, aluminum, oxygen, phosphorus, nitrogen, hydrogen potential, and also this another one. And with this kind of 6-element potential, we can do the zeolite database. For example, in the zeolite, people actually generally didn't know where the acid or proton reside in this kind of zeolite framework. But with our code, we can do very fast calculations. We can simulate this kind of hydrogen or proton acidity TPD spectrum to compare with the experiment. We can exactly define where the proton is in different zeolite materials. And another database we are working on is this kind of metal phosphorine database, because we know many organic chemistry are very interested in one metal atom in the center and then with some ligand outside. With this kind of ligand, they can do many, many reactions. So in this case, we just submit papers. We try to understand why Suzuki reaction cannot say very easily to do this kind of reaction with the chlorine atom on the benzene. Then we have used our database to find the material, find the ligand to find. Eventually, we get several very cheap ones to compare. And the experiment has confirmed this one is the real good ligand to do this Suzuki reaction. And for the catalysis, I give you this example. In catalysis, we didn't know material exactly in many, many cases. So for example, in this zirconium chromium oxide, we have 3 elements, but chromium has a variable, say, oxidation state. In catalysis, people generally didn't know what's really going on in this catalysis. So for this kind of case, if you do DFT, this one need to be PB plus U at least. And it's being polarized. It's very, very slow. Basically, you cannot really going on, say, going very far away upon these kind of very simple calculations. But using this kind of automatic active learning, we can use some like 1,000 CPU cores. Nowadays, it's not very expensive, but 3 years ago, it's still very expensive. And it takes about 2 weeks, and we can generate more than 38,000 different structures, and this is the accuracy we get for the training. And eventually, with this kind of potential, we can just kick off to do many, many different points in this kind of ternary phase diagram. For each point, that means you have a different chromium and zinc and oxygen combination, and you can use SSW and NN approach to find the global minimum, define the thermodynamics of the bulk, and then you do the surfaces, and eventually you found this one is very good, which is a very strange combination. So at that day, I told the colleague, say, we take 1 month, but if you do DFT, it will take 100 years. So everyone thinks this is a very good progress. So finally, I will show you some our work for this kind of GCMC combined with SSW. We know GCMC is a good technique to do this one, but everyone knows this one is very slow. So if you want to move atom and then you evaluate this system to compare with this energy, so this is a GCMC scheme. So every time you move atom or delete atom, add atom, you have to use this kind of statistic to govern your change of your system. But this typically too slow because 1 atom is just too small for a big system. So we generally use a parallel one and we use SSW to speed up the search. And use this kind of approach, we can to understand this kind of silver oxide oxidation. So my student Dong Xiao is also here. He posted a poster yesterday and talking about this one. He developed this method we call automatic search of optimal surface phases, uses this kind of combined GCMC and SSW approach to find a different surface oxide phase of silver. And with this one, we can eventually identify the ethylene oxidation surface active site. We find a very interesting 5-coordinated oxygen beneath this kind of silver atom, and this silver atom is a key species to promote this kind of ethylene epoxidation. Okay, I still have some time, so I just go ahead. This could be a very long story because Fischer-Tropsch synthesis is also another very, we call the long history or ancient topic in heterogeneous catalysis. But this one is really, really complex with this many different products and also catalyst structure. So basically, it's like this. You have the syngas. We call this as a syngas, CO and hydrogen. And with the iron as a catalyst, you can get a very long chain hydrocarbons. So this one is particularly useful for some countries without oil, for example, China. So our companies in China invest a lot to improve this technology. But there are many problems. For example, this catalyst typically is not very stable because under the syngas condition, this kind of oxide becomes this one and iron, and the catalyst should be like this, a mix of these three, and it's not very stable under reaction conditions. So there are actually many, many studies in this topic. People want to understand which one is the active site and which one is the active phase. And the different experiments actually give you a different story. Someone said it's iron 5 carbon 2 is the best, and another one said it's carbon iron 2 carbon is the best. And from the XRD of the intermediate, you can see it's not very sharp. So basically, it's a mix of all these different phases. Theoretical calculations also has been done by many groups, but you can see even for iron 5 carbon 2 nanoparticles, there are so many different nano facets. And if you want to explore all these reactions on all these facets, it will be a huge task. It's just too expensive using the DFT calculation. And I also want to remind you, the iron-related calculation is spin polarized. It's very slow. So these kind of issues are quite typical and very difficult to proceed in catalysis. And people want to understand the active side, want to understand how this kind of long-chain hydrocarbon grows, and eventually to see the kinetics rate determined step, and we also have the ASF distribution. To give a short story, we just follow a very standard approach which has been used by my group for the last few years. Basically, we do not rely on any experimental input. We just believe this is iron carbide, and then we do this kind of thermodynamic analysis to search the global minimum. Eventually, we can find this 4 has the global minimum, which at the, say, we call the convex point of this diagram. This means these 4 phases are possible to present under reaction conditions, and at the reaction conditions, the chemical potential of the carbon actually is variational. So basically, it can be 4 and also can be 1. So this explains why this experimental, say, iron carbide is a mix. And we also can see the different structure of different iron carbide. It's really complex and many, many different chemical environment for different carbon and the iron. I just pass all this slide because all this paper has been published. After the bulk search, we just do the automated search of all the surfaces under the reaction conditions. You add the carbon in and delete the carbon out. And you using this kind of grand kinetic Monte Carlo simulation, eventually you can see different surfaces reach to this kind of saturated termination. For example, 071, iron 7, carbon 3. And all these surfaces are very, very similar, even on different, say, bulk structures. And this is the final Wolf construction from our surface energy. We can see the top surfaces has a reasonable distribution, and then we do this kind of simulation to find the pathway. So how we find the pathway? Basically, it's also automatic. What we've done is to fix the transition state structure, like CO dissociation. We fix the distance at about 2.0 angstrom, and use this kind of transition state night complex to probe the surface condition. We put this kind of molecule on the surface and do SSW to search the global minimum. Eventually, the carbon atom or hydrogen atom nearby will respond to this kind of transition state complex to give you the lowest energy transition state. And finally, we can do all these reactions one by one. And eventually, we find that the active site is like this one. We call the AP5 site. And all these carbon-carbon coupling reactions has been determined. The barrier actually is very surprisingly low. Only for the carbon plus CH is only 0.5, and this is only 0.4, and everything occurring very cloudily locally at this kind of AP5 site. Finally, we can do this different coverage and the reaction profile. So I just go quick because this is just everything with the data. You can generate this kind of graph to understand the kinetics Happily, we found some isotope experiment many years ago, about 13 years ago. They actually find this kind of intermediate. This is an indication the carbon-carbon interaction is the correct one. And this is the kinetic analysis. So I just pass everything for the Fischer-Tropsch. I go direct to the take-home message. So I believe for the ground state calculations, so not excited state. I know every time people will ask me excited state, we didn't know excited state for our LASP code. For ground state calculations, LASP code can give you a huge benefit. You can do many, many different materials with many, many different reactions. And we also find this kind of database facilitate catalysis search. Basically, we use the energy as the volcano curve. We think this is the future for the catalyst design. So finally, I will thank my team. Also, thank you all for your attention. Thank you.
Thank you very much. So, any questions?
Yeah, very impressed talk, Zhi-Pann. So regarding the SSW, you said it's borrow some nice ingredient from metadynamics. So my question is, does it also inherit some limitation from metadynamics, which means that you have to choose actually predefine the reaction coordinates when you do the searching of your potential energy surface?
Yes. So I think that's the drawback for metadynamics, but not the drawback for us, because we use the random search. We didn't need to say, find by ourselves or design by ourselves for this collector variable here. So basically, we use the Cartesian coordinate to generate a random number and use this kind of dimer. We modify the dimer approach to soften this kind of a mode and use this mode we add in the Gaussian and we do the local. So everything is automated. So there is no particular or you need to design some kind of
All right. Yeah, very impressive talk. So I was interested in your many-body function after the the output of the atomic contributions. So how does that cost? I mean, you have shown in one of your slides the comparison of the accuracy and the efficiency, but that depends on the implementation of different codes. So yes. We know SSW-NN is pretty slow actually in the yes. Different variants of message passing neural networks. But I mean, in general, that's a clever, smart way to accurate sum those atomic energies in a different way, just by direct sum, right? You use many-body formalism. So how does that compare to the message passing network, the framework? I think both framework can add some like many-body information or non-local information. So I guess my question is, which one is better in principle? Yeah, not in numerical.
So
thank you.
This is a very interesting question. We have been think about this one for something like 1 year since we have this kind of scheme. Initially, my student, because this code are available and written in Python, it's very easy to test or run by our student. And what the feeling they get is very slow. And they said because they have the three-body or this kind of high level of equivalent implementation. I think all this boils down to the first thing is you have to include this kind of three-body or some kind of you can see equivalent implementation. So this kind of things typically is quite slow. So if you have many these kind of many-body functions, it will become slow. So this will be the same. But for us, I think the basic thing is this one is some kind of supplementary. It's not like say feature extraction, role in this kind of MPN or graph network. So this one for us is something kind of oscillatory, or you can take that as something like because there is a shortcut as to here, this black line. So parallel approach or this kind of atomic-based approach still have this kind of total energy contribution. Typically, it's a larger part. And all this one, we just want to make this kind of long range or local range kind of calculations to give you the trivial or minor addition for this kind of long range or reactions. So basically, we did not use a lot of many body functions. So we only have typically 5 or 10 or this kind of no more than, say, 20 these kind of functions. So we use very cheap implementation to give you the same, say, long range effect. Otherwise, if you use the graph network, you want to go to long range. So you have to 1 ring, 2 ring, and this one have to be implemented for every atom and for every net, and it becomes slow. So this is the key difference. We just want to use this kind of local as the major energy contribution, and all this one as some trivial or minor adjustment for the total energy. So that's
yeah.
our scheme. Yeah.
Thank you.
One final question.